Welcome back, ladies and gentlemen. In this video, we're going to look at some examples of how to calculate work, and we'll see some of the details that do matter when you're trying to do this. So basically, recall that work is equal to force times distance. But the thing is, the direction of the force and the direction of the distance traveled both matter. So let's look at a couple examples here, just real quick. I'll do a Freebody diagram, and we can have an object here, and it has weight. So there's the force of gravity. Well, what if this object is traveling in this direction? So do a different color so it stands out. And this arrow does not represent a force. This arrow represents a motion, the direction of the motion. So it's traveling that direction. So there is the direction of the displacement. And the thing is, what you have to do is ask yourself, well, this force is a vertical force, or it's at least in the direction of this axis, whatever this axis might be, usually the y-axis, right? But there's this vertical force, but there's no vertical motion. So this force will not be doing any work on this object because of the lack of any movement in this same direction. So it's moving this direction. Well, if there's no force also in this direction, then no work is done. So this totally matters. Let's contrast that with a slightly different situation. What about this object? It's got weight in that direction. And what if it is also moving in that direction? So I'll put this arrow right next to it. So it's going to move in that direction there. This might be a situation where something is falling and weight is the only force acting on it. This might be a projectile, might be free fall. And so it's moving downward, the force is downward. Well, then this force will be doing work on that object. So what if the situation is not so clear, right? We can sort of make general statements about things. And it turns out when we make a general statement, it usually ends up making our job a little easier even. So what if we have a force in this direction, just whatever force is acting on the object, right? Call this our y-axis, our x-axis, that's fine. And this force is at some angle with respect to that x-axis. There's angle theta. But at the same time, while this force is applied, what if the object is moving in this direction? So it will have a displacement there. Aha! So in this situation, we have to concern ourselves with two things. We need to look at the components of this force. There's the component in the y direction. It basically goes as high as the tip of that arrow, and the component of that force in the x direction is there, and it goes as far as that. So check it out. Now, by breaking up the force into components, we can start to say, well, this guy is vertical, but there's no vertical motion. This part does no work. This component of the force is in the same direction as the movement, and so that component is doing work. So the force is getting some work done, but we don't use that whole value of the force. So check this out. You can kind of see a right triangle that we've created here. And if I just kind of redraw that triangle, there we go. Here's angle theta. And here's the force. Well, remember, it's this component here. It's that component that we're concerned with. That's the side that is adjacent to our angle. So this is going to be hypotenuse times cosine of theta. This is the business that's doing the work. And so if we know this, and we also know how far the object moves, then we could use this to calculate the work, right? So, for example, let's put some numbers to this. Just going to do a quick redraw so we can have it in front of us. We have this force. We have our angle theta. And it is moving in this direction. Okay. So, if the force is 50 newtons, let's just give it some nice round number. And if the angle theta, let's just say, I don't know, 41 degrees above the horizontal, and the object moves in the positive x direction, then we could, well, let's give it an actual distance. Let's say its distance in the x direction is, I don't know, 10 meters. Something easy. So what are we going to do? We want to find the work done. Well, first of all, we have to ask ourselves, is any work done by this force? There is a component of this force in the x direction. It does not have to be in the same x direction, but it is in the x direction, right? This force could be up this way. It might have been acting like that. In which case, this force would still have a component in the x direction, just in the negative x direction, right? And it would still be x, and so it would still work out, but we're not dealing with that right now. Work done. Okay. Well, it's force times distance, but the force we're concerned with is only the horizontal component, or the x component, x and y, of that force. The x component is force times cosine of theta, and, excuse me, we have to multiply by the distance, right? So we have the force is 50 newtons. The angle is, we said, 41 degrees. And the distance, we said, was 10 meters. So, handy dandy calculators out. The work done by the x component of that force would be 377 newtons. Easy. So this is why you're going to see this business of a cosine of an angle in the equation for work. What if the force, just real quick, what if the force was already entirely in the direction of the motion? So there's our force along the x-axis, and we said, well, that is also the same direction that it's moving. I'll label that, and I'll label the force. Well, think about this. What's the angle between those two things? In this case, the angle between those two arrows is 0 degrees. What's the cosine of 0? And cosine of 0 is just 1. So when they're actually in the same direction, truly in the same direction, this equation goes back to just force times distance. Use the whole force. All right, well, another example. Let's check it out. So in this example, let's talk about one of those suitcases that has a handle on it, and you just kind of pull it along behind you. It's got a little wheel at the base of it. So here's your suitcase, a little handle, and this rolls along the ground. And it's going to end up some other location. Okay. So we're going to apply a force to the suitcase, generally by pulling up on the handle. There's our force. Let's call that 22 newtons. Now this force is parallel to the handle here, and so we have this angle theta here. Let's call that angle 52 degrees. That might be kind of typical. And finally, we have to know how far this thing travels. The distance will be, I don't know, 8.5 meters. Not too far, but a good distance. We want to find out how much work is done on the suitcase. So we're going to use that work done is force. And here's the more common way of writing this equation right here. The more common way is to write force times distance times cosine of theta. We just rearrange it a little bit. There's no real reason for doing that. except it's just more traditionally seen this way. All right, well, we have our information. The force is 22 newtons. The distance traveled is 8.5 meters. And cosine of 52 degrees. And when we work that out, we get, well, okay, 115. And turns out cosine of 52 degrees really has no units, so this is newtons. And this is meters, so Newton meters. But a newton times a meter in cases of work or energy, to that, is a joule. So we have 115 joules of work done on the suitcase. Easy peasy, right? We need the angle, we need the force, and we need the distance traveled. Cool. But note something here. When the work is done by multiple forces, you can find the net force and calculate the work done, or you could find the work done by each force and find the net work done by adding up the work done by each force. So that's actually going to be the next example. Check this out. So here's our situation. Your teacher lifts an object of mass 11 kilograms vertically through a distance of 0.90 meters. And we're going to say that your teacher was lifting this object. It was moving at a constant velocity. Constant velocity. So this tells you a whole bunch right here. Constant velocity means that acceleration is 0. And when acceleration is 0, net force is 0. And that means all forces are balanced. What we want to know is how much work is done by each of the forces that's acting on the object. So we have this object. And it's simply lifted. There we go. This distance of 0.90 meters. All right, and so how much work is done by each force acting on that object? What are the forces acting on it? Well, essentially, it has weight, of course, force due to gravity, but also it would be supported by your hand, lifting it up. There's a normal force. You might call it an applied force, but it is a normal force. No question. And why did I draw those arrows the same length as each other? Because I know they must be balanced. Now, when they're balanced, then that normal force is equal to the force of gravity. Well, the force of gravity is equal to mg. And I can start to work out a whole bunch of stuff. How much work is done by each of those forces? Maybe I should call this one force 1 for the sake of simplicity, and this one force 2. Okay, so I want the work done by force number 1. Well, okay. I have to keep this in mind. Which way is it moving, right? It's moving in that direction. So I will use force times distance times cosine of the angle between the force and the direction of the motion. The force, well, it's the normal force, but it's equal to the force of gravity. Force of gravity is mg, and that's cool because I know both of those values. So I'll just write mg for the force. Distance is my distance, no big deal. So here's what the equation turns into, and now I can plug all my numbers in. The mass was 11 kilograms. G is 9.8 meters per second squared. The distance is in the upward direction, a positive 0.90 meters. And finally, cosine of the angle between them. Cosine of, well, the angle here is 0. Okay. And when I do that math, I get a number that rounds to 97 joules of work by force number 1. I had to use force number 1 here. That's one of the answers that I needed to find. So now I also have to find the work done by the other force, force 2, which is gravity. I think I have enough room here. I'll squeeze it in. The work done by force 2 is force 2 times distance traveled times cosine of the angle between them. Force 2 is mg, so I essentially have the same values I'm going to plug in for this, so it'll be 11 kilograms. Oops, kg. That's an 11 kg, sorry. Distance is 0.90 meters. Oh, sorry, I forgot g. There we go. 9.8 meters per second squared. I'm just going to put it here, and it's fine, even though it's out of order. And finally, cosine of theta. Now this is where it's different than the previous force. Here, the force is downward and the motion is upward. The angle between those two things is essentially 180 degrees. That one's pointed up, the other one is pointed down, 180 degrees apart. That totally matters. That's going to change the answer here. It's not going to change the number, but it turns out it puts a negative sign in front of it. Cosine of 180 turns out to be -1. So I still get a number of 97, but it's -97 joules of work done by force 2. Well, that's interesting. Okay. So what is this going to do for us? What does this mean? All right. Page 5 here. Remember from the previous video, we had this equation that work is equal to the change in an object's kinetic energy. And kinetic energy is the energy of motion. So if its motion is changing, like if its speed is changing, really, then work was done. However, there's something important about this. This is a very important equation, by the way. It has a name, in fact. It's called the Work-Energy Theorem. When you hear about the Work-Energy Theorem, that's it. Here's the issue, though, the thing to keep in mind. This work is not the work done by any single force. It's the total work, or the net work. The overall amount of work done. Well, think about this previous problem. What was the overall amount of work done? We'd have to add the work done by force 1 to the work done by force 2. So we're going to analyze this and say that the net work is just the sum of all individual work. So we're going to add up. Remember, that's the sum of things. Add up all the work done by various forces. That's going to be work done by force 1 plus work done by force 2. And we know that that's 97 joules plus negative 97 joules. And that gets us 0 joules. Okay, so this is something we know about the previous problem also. The net work done is 0. Well, what does that mean? For our object that your teacher was lifting, it means that since no work was done overall, then by how much did its kinetic energy change? Change in kinetic energy was 0. There was no change in kinetic energy. It was not speeding up. Well, that makes total sense. It was not speeding up, constant velocity. Net force was 0. So these things are connected. This is real important to see. The speed of the object has not changed. Okay, that's it for now. Thanks for watching. I will catch you next time.